Morning, folks. We are starting Chapter 8 today. Before we do, a couple of quick announcements. The first and foremost is that, of course, the important thing is Wednesday is our next exam. This is on Chapters 6 and 7. Note that I have posted a study guide in the equation sheet on Brightspace. The study guide in particular has information about what problems will be useful for you to study. And it is actually one problem from the Exam 2 practice and one problem from the Exam 3 practice. So keep that in mind. They're actually kind of spread out. This is because this semester we're trying a new textbook and the units are all messed up. We're also doing more exams, so it's a little bit scattered. It doesn't line up with any exact exam that we've given in the past. Suffice to say, Chapter 6 includes things like energy, potential energy, work, conservation of energy, and so on. Chapter 7 includes momentum, center of mass, conservation of momentum in collisions, and use that to your advantage as you are prepping for Wednesday's exam. The other announcement about that is I have expanded my office hours today and tomorrow slightly. I've added 2 extra hours of appointment blocks this afternoon, and I've added a 1 hour of walk-in office hours during my Tuesday, during the normal 11 to 12 time slot. I have limited availability outside of that. If there's a really pressing issue that you would like to address in a meeting, you can shoot me an email. We might be able to work something out. But that's the general plan. I will be sending a sign-up sheet for the evening exam, as I usually do. That will be up today. And we're probably going to need it by, let's say, 5 p.m. tomorrow. Expect that soon. And otherwise, it's this is third time around, so hopefully we're comfortable with how it goes. A couple of notes about Exam 2, which I finally did get back and graded. Got back to you and was graded. I apologize for the long delay. Last week was a nightmare. My weekend prior was entirely disrupted, but I am finally caught up now. And that includes with your exam grades. By and large, I was really happy with what I saw. General performance was much higher on this exam, or much better, much more consistently better than it was on Exam 1. So kudos to you folks. Whatever you're doing, it is working. Unfortunately, the practical result of this was just that I scaled everything a little bit less. And that's consistent with our general sort of grading policy for this class. Now, with that said, I do want to, caution you that if you were successful, continue building that, and if you weren't successful, don't lose hope. We still have time left. The final exam is optional, and it can stand in for a lower exam grade. There's still time to improve. No exam is a make or break in this class. You can still get a good grade, even if one of your bad exams grades gets kept. But it does require that you spend some time really focusing on what's working for you during your preparation. If you have now tried 2 different exams and you've gotten the same result each time, that suggests that maybe whatever you're doing to prepare isn't quite working right. So I'd suggest you try to mix it up. If you were watching lots of videos, maybe leave the videos this time. Don't spend your time going back through the lectures. Spend your time trying practice problems. If you were doing tons of practice problems, but you found yourself getting tripped up by the wording of the problems, then maybe what you should try to do is just go to the back of the textbook and just read. Just read all of the problems at the end of each chapter, just so you can get an idea of how different questions are asked. Try to find something to improve your study techniques. Don't just try the same thing over and over and over if it's not working for you. By contrast, if you have found something that works, latch onto it and never let go. Just keep doing what you're doing to try to maintain your success moving forward. Okay. Today, though, we are moving on to Chapter 8. And I need to quickly edit my slides on the fly. That's rotational motion. Chapter 8 is not on Wednesday's exam. So if you are worried about new information, standard disclaimer. You can pause this lecture, come back to it after the exam, and you'll be fine. I want to mention, though, that Chapter 8 is our longest chapter because for some reason the textbook author decided to put 2, arguably 3 chapters worth of material in one single chapter. As a result, we're actually going to be spreading Chapter 8 over 4 lectures. Today, Friday, the next Monday, and next Wednesday. I do also want to mention, I will do a little bit of civic awareness. A week from tomorrow is Election Day. Now, I'm not going to talk about politics. This is a physics class, not a politics class. But I do want to encourage all of you to, exercise your right to vote, whether you are doing so via mail-in ballots, early voting, or taking the day on Tuesday to actually go and vote. Whatever your social situation, whatever your political beliefs are, you are amongst a generation of people who will define the policies that we're going to be living through over the next 20 or 30 years with any luck. But that will only happen if you remain active and you let your voice be heard. I know it can be discouraging, the idea that your individual vote might not carry much weight and that the outcomes from elections might not be what you personally necessarily want. The only way to combat that is to vote and to let your voice be heard. Because if you do that collectively, then maybe you won't be so disappointed when the results are finally announced. So I'll probably make that reminder a couple of times, but please, if you are able to, if you are a U.S. citizen and you do have the ability to do so, please vote between now and next Tuesday. And if you're worried about it, hey, guess what? Election day, you get it off. We have no classes on Tuesday. So if you want to go vote in person, if that's the way you prefer to do it, then you have that option. There's nothing standing in your way, certainly not me. And if we see a large percentage of activity of students voting, maybe I'll try to do something special for you by way of a celebration of exercising your civic duty and your right to vote. All right, that's my little public service announcement. I'll probably poke at it a little bit now and then over the next few days. But for now, we have to get to this. Nope. That's not how this is supposed to be displayed. Try that again. Nope, okay. Enjoy this apparent advertisement for Borat, the new Borat film, I guess. Thanks. There we go. Okay, this is what I was trying to get at. Chapter 8, it's rotational motion. We're talking about things that are moving in circles, rotating. This is in contrast to all of the motion we've talked about so far, which has broadly been linear. The only exception to which, of course, being centripetal acceleration and centripetal forces, which we talked about a little bit in Chapter 3 and Chapter 4. In Chapter 8, we're really delving into rotational motion in earnest, and there is a lot to cover here. Today, and I want to mention, I'm doing this slightly out of order from the textbook, which means for this chapter in particular, depending on how Dr. Tamaro does it, you might get out of sync. My impression is that he'll probably do it in the same order I am, but I haven't confirmed that with him yet. So you might want to just keep that in the back of your mind if you are one of the many students who attends both lectures. We're going to study rotational kinematics, then we're going to talk about rotational energy, then we're going to talk about rotational dynamics, those are like the equivalent to forces, then we're going to talk about rotational angular momentum. And if you have noticed those 4 topics, kinematics, energy, dynamics, momentum, those sound familiar? It's because those are the same things we've been talking about in terms of linear motion. So Chapter 8 is really the chance for you to test and understand whether or not you have a firm grasp on the material that we've talked about up till this point. Because we don't ever retest on chapters, but a lot of the concepts from Chapters 2 and 3, Those are going to be relevant in the first section of Chapter 8. Chapter 4 and 5, that's the third section of Chapter 8. Chapter 6, that's the second section of Chapter 8. And Chapter 7 is the last section of Chapter 8. So this is a boiling pot where we take all of the lessons that we've learned thus far and we apply them to a slightly different type of motion. Now, to that end, we're going to start off with the same place we started off before, which is kinematics. We're going to do rotational kinematics, which is the way we describe the motion of objects that are rotating. What do I mean by that? Well, in Chapter 2 and 3, we talked about all of the kinematic variables: position, displacement, speed, velocity, acceleration. We're going to take all of these concepts and we're going to apply them to the case of what is called rigid body rotation. Note, when I say rigid body rotation, I mean an object that is solid and is rotating. This is in contrast to an object that is flexible in rotating. And it turns out that that rigidity, the first word in this expression, actually really simplifies the math to a point where it's actually doable. And the way we define rigid body rotation is, one, the shape of a rigid body doesn't change. It remains fixed. And, importantly, when one part of a rigid body rotates, all of it rotates. So, for example, I am not a rigid body. I can rotate my arm, and my other arm does not rotate. By contrast, if I take a rigid body like this baseball bat and I rotate it, note that the whole thing starts rotating. There's no part of it that is not undergoing rotation, with perhaps the sole exception of the center point around which everything is doing the rotating. Importantly, the final thing about rigid body rotation that we're going to deal with in this class is that if you were to take any individual part of a rigid body and you were to trace out that individual point's path, it's always going to trace out a circle. Let me show you an example. Here we have a wind farm fan, a wind turbine. That's the word I was looking for. And I'm just indicating a couple of points on here. I'm indicating in this light orange one the point at the top of the blade, and I'll pick out another point here in the middle somewhere just to give you two different points. If I let time go forward and I just track the path that those points trace out, as the whole thing rotates, note that both of those points trace out a circle. That is indicative of rigid body rotation. Now, we're going to go through the exact same process that we did in Chapter 2 and 3. We're going to start with position. We're going to turn that into displacement. We're going to turn displacement into a velocity, and velocity into an acceleration. The only difference is we're using slightly different variables to describe each of them. To measure one's position during rotation, it is not useful to talk about x and y coordinates. Instead, you want to talk about the angle at which an object is relative to a reference point. We specify an object's initial position with theta naught and its final position with theta. And as a result, if I say, for example, take this fan which is rotating, I can define an initial position relative to some reference line. Note that the center point here, which is the point at which everything is rotating around, is given a special name. It's the axis of rotation. Note that it is called an axis because although it appears to you as a point that everything is rotating around, it is actually a line. Hence, it is called an axis of rotation. If you consider I were to take this baseball bat and I were to rotate it around its center, note that all points along the baseball bat are rotating, and so the axis is the center line down the center of the bat. Okay. So initial position is measured up from a reference point at some angle theta. Some later position is measured with a new angle relative to the same reference line. So note that my angle has increased from theta naught to theta. And I specify this difference up here as the change in theta, otherwise known as the angular displacement. We measure angular displacement as a change in theta, final minus initial, and it can have a direction, either clockwise or counterclockwise. Here, theta is changing in this direction, which is counterclockwise. If theta was changing in the other direction, it would be clockwise. So right away, angular kinematics are actually simpler than regular kinematics. The reason being is they are only ever one-dimensional. Theta can either be clockwise or counterclockwise. Those are the only two directions, which helps simplify our problems a lot. Now, it's worth noting that in this chapter, we will often be measuring angular displacement in terms of the unit of radians as opposed to degrees. Now, sometimes you will see us use degrees. Sometimes you might even see us use revolutions. If I go around a circle once, that is 1 revolution, 2 revolutions, 3 revolutions, and so on. If you've ever seen a car and you have a tachometer in your car, you'll notice that the units of that are RPM. Those are revolutions per minute. But for our purposes, the physical unit, meaning the one we're going to want to default to, is actually the radian. So this is different from before, and you'll want to keep that in mind. Now, at this point, it's worth mentioning how we define a radian, and it's in terms of the so-called arc length of an angular region. Here I have a circle, and if I draw a radius here and a radius here, note that the angle between them is theta. I can calculate the length of this segment, called the arc length, which I refer to as S. I don't think your book actually gives it a variable. But this arc length here can be calculated by taking the radius of the circle and multiplying it by this angle theta. Now, this angle, in order for this to work, theta has to be measured in radians. You cannot calculate an arc length if you use degrees. It just doesn't work. It doesn't mean anything. This is why we always have to make sure that we're using radians in this chapter. And so if you're given, for example, 360 degrees, you're actually going to want to convert that to radians. Similarly, if you're given revolutions, you're going to want to convert that to radians. Think back to Chapter 1, Dimensional Analysis and Unit Conversion. You're going to have to do that from time to time here. And I've given you these conversion factors. 1 revolution, 1 complete path around a circle, is equal to 360 degrees, which is equal to 2 pi radians. And that's important. Note that this tells us if I take my theta and I go all the way around back to the beginning, theta all the way around, theta becomes 2 pi. Note that the arc length becomes r times 2 pi, or 2 pi r, which is precisely the circumference of a circle. That's where the circumference formula comes from. There's a question in the chat, will you have to switch your calculator to radians mode? Yes, absolutely yes. If you are doing work with radians, you will absolutely need to switch your calculator to radians mode. 100%. I'm really glad you asked that, because it is very important that your calculator is in the right mode. If you're working with degrees, it needs to be in degrees. If you're working with radians, it needs to be in radians. Yes, absolutely. Now, it's worth noting that we define an angle of 1 radian as the angle here such that the radius is equal to the arc length. This right here is the definition of a radian. And here's just a reminder to make sure your calculator is in the correct mode. Okay, now that we have our units, how can we take our angular displacement and turn it into kinematics? Now, the next 4 slides are going to go by lightning fast because we've done them before. Our average angular velocity will be our angular displacement divided by time. We use a different symbol. Instead of v, we use the Greek letter omega. Please do not call it a w. It is not a w. It is the lowercase Greek letter omega. And it's just the displacement divided by time. It has units, its base units are radians per second, but of course we can see other units that are common. Revolutions per minute, I already mentioned those. You might also see something like degrees per second. And if you get something like this, you're going to want to convert to radians per second unless the problem really doesn't need you to. The direction is measured the same as the displacement. Your angular velocity is either counterclockwise or clockwise. Now this is of course just an average velocity. We know that if we take the limit as t goes to 0, we could get the instantaneous angular velocity. This is the exact same thing that we did back in chapter 2. And when we're talking about an object's angular velocity, this is really what we mean. We're talking about its angular velocity at a specific instant in time. And so we just use the symbol omega for that. Once we have omega, we can define an average acceleration, which is the change in angular velocity over time. Now, we use a different symbol for this. This is the Greek letter alpha. And we can calculate the average angular acceleration as the change in omega over change in time. The unit here is radians per second squared. And once we have an angular acceleration that is on average, we can calculate an instantaneous acceleration, which is what we usually talk about. Of course, in this course, we limit ourselves to situations where alpha is constant, in which case the average acceleration is equal to the instantaneous acceleration. So we have a bunch of new variables, and I've just listed them for you in this table here. There should be a delta here. I apologize. Angular displacement is change in theta. Theta minus theta naught. And we could also have initial and final angular velocities using the Greek letter omega. Angular acceleration using the Greek letter alpha. And note that the elapsed time is unchanged. That still uses the variable t. If this looks familiar, it's because it is extremely similar to our regular linear kinematics equations, x, v, a, and t. In fact, there is a 1-to-1 correspondence for every linear quantity that you dealt with in chapter 2 and 3. There is an equivalent angular quantity. Theta is the equivalent to x. Omega is the equivalent to v. Alpha is the equivalent to a, and t is the equivalent to t. This should suggest to you that all of the intuition we developed in chapter 2 and 3 should translate directly to chapter 8. And sure enough, it does, in the form of these new rotational kinematics equations. These are the equations that relate angular displacement, angular velocity, and angular acceleration to each other through the unifying feature of time. So this might seem troublesome to you, because now we have to remember an entire new set of equations, right? Well, no, because the rotational kinematic equations are functionally identical to the regular kinematic equations. In fact, if I just replaced, oops, that should be red. If I just replaced every instance of v with omega, if I replaced every instance of a with alpha, and I replaced every instance of x with theta, these equations are identical. They are literally the same equations. And so everything we did in Chapter 2 and 3 has a one-to-one correspondence to what we're doing in this section of Chapter 8. And so we can use the same problem-solving strategy that we used before. We draw a sketch and label everything. We determine known and unknown variables. We find equations that relate them. We rearrange the equations to solve for the unknown, then enter values, and do sanity checks at the end to make sure we're on the right track. Just something to keep in mind is just like before, because some of these equations are quadratic, meaning they have factors of a variable squared. Sometimes we have to do square roots, and so sometimes there are two answers, one positive and one negative, and you'll have to infer which one is the correct one. Always choose the answer that best fits the situation. With that said, I think what I'd like to do is a couple of practice problems. And then I'm just going to kind of tie everything together, and we'll call it day one here on Chapter 8. So, in this problem, we have a variable speed window fan that is switched from the low setting to the high setting, during which time the angular speed of the blades increases from 28.1 radians per second to 58.5 radians per second, while turning through a displacement of 93.1 radians. Note that I added in the word displacement that is not there. I get that from context clues. The units here are radians, which suggests this is a measure of theta, and I know theta is a measure of angular displacement. So we want to know what is the magnitude of the angular acceleration, and then we want to know how long it takes the fan's angular speed to change. So, you know, maybe I'll just draw a little window fan that's going to look like a really bad flower-looking thing. It's worth noting, I didn't say this explicitly before, but I'm going to do so now. Our convention is for counterclockwise to be positive and clockwise to be negative. That's just a convention that we use. So here we have a fan that starts off with a small angular velocity omega naught and ends up sometime later with a larger angular velocity. And we want to know what the angular acceleration is, assuming that during this time it accelerates through a displacement of 93.1 radians. So this is the same game we used to play. I know that I'm trying to solve for acceleration, angular acceleration, that's the Greek letter alpha. I know that I'm given the initial and final angular speed, and I'm given the angular displacement theta. There should be one more variable here. Sorry, theta naught. Now, at this point, we have to pause and say that while we are given the total amount of change, we actually don't know what the initial and final angles are. We just know the difference between them. This is something we can address by setting our reference point as whatever that initial position was. So we're just going to specify that our initial angular position is 0, because we're always free to set our reference point. And that's going to allow us to find our final angle. And that will just be equal to the displacement. So looking at my variables, I want to find alpha, so I need an equation that has alpha in it. Good news, they all do. But the only variable I don't have is t. So I can't use any equation that has t in it. So that one's not helpful. And that one's not helpful. Which just leaves me with this one right here. So that's the one I'm going to use. Omega squared equals omega naught squared plus 2 alpha, and I'm going to call that delta theta. Subtract the initial velocity over to the other side. Divide both sides by 2 delta theta, and that's going to give me alpha. I can plug in my values. Note that they're already in base SI units, radians and radians per second. So that's going to be 58.5 squared minus 28.1 squared divided by 2 times 93.1. Plugging that into my calculator, 58.5 squared minus 28.1 squared divided by 2 times 93.1, assuming I haven't made any silly errors anywhere, that gives me an acceleration of 14.1 radians per second squared. And that's the answer to part A. Now part B wants us to find how long this takes. So part B wants us to find t. At this point, I have everything except t, so I can use whatever equation we want. So I'm just going to use this one because it's easy. Omega equals omega naught plus alpha t. Omega minus omega naught divided by alpha equals t. So that's 58.5 minus 28.1 over 14.1. 58.5 minus 28.1 divided by 14.1 gives me t equals 2.16 seconds. And if you've ever used a window fan and you've actually turned on the knob, you've heard a whoo as it kind of winds up. And yeah, it seems like 2 seconds to go from low to high. That seems reasonable. But note that the process that we used to get here is functionally identical to the process that we used to use back in Chapter 2 for one-dimensional kinematics. Let's try another example. This is a good example of a problem that gives you very little information, but you're still expected to be able to figure it out. We're told at 6 o'clock, the minute and the hour hands of a clock point in opposite directions. What is the first time after 6 o'clock that the hands point in the same direction? So, to this end, we actually have to depend on our ability to work with an analog clock. Now, I know this is something that is a little bit out of vogue these days because most of us tell our time with, one of these. Our phone, and it just tells us right there, look, nice, 10:35. Well, it was mirrored for you. If you are a person who has, for example, a smartwatch, you may want to, for this particular chapter, get some familiarity with how these old-style analog faces work because they're a great topic for problems that we can ask you. Now, at 6 o'clock, or well, I guess what I should say first is that 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Those are the times on an analog clock. And at 6 o'clock, the hour hand, which is the short hand, points down. And the long hand points up. we want to know the first time after 6 o'clock that the hands point in the same direction. And to that end, let's imagine what's going to happen here. Now, the way a clock works is the minute hand changes, and I'll use my pencil for that, changes rapidly, and the hour hand changes slowly. So what's going to happen is they're going to rotate at different speeds, and sometime later, the minute hand is going to catch up with the hour hand. And that's ultimately the point that we're looking at, that we are looking for, is what is the time when the hour hand and the minute hand are at the same location. Notice that I have given you no information here except that both hand turns at a constant angular speed, so the acceleration is 0. This means no matter what equation I use, the term with acceleration is going to go away. In problems like this one, we are meant to, 1, infer as much information as possible, and 2, try to relate variables to each other to make the problem a little bit more straightforward. Now, looking at these, we know the acceleration, and that's fine, that's not going to come into play, and we want to know time. So the question becomes, of the rest of these, what do we know things about, and what can we infer? Now, right away, I'm going to point out that we need to specify a reference point. This is to say, we need to specify a location where theta equals 0. Now, I'm going to choose theta equals 0 as being the vertical line here. This is going to be my reference point, which means that my minute hand, I should do that in orange, starts at theta naught equals 0 radians. And it's going to end up at whatever this final theta is. Now, I don't know what it is, but I know it's going to end up there. Similarly, oops, I need to give myself a little bit more room here. Similarly, the hour hand, I know that it starts relative to that initial blue line, it starts at a non-zero angle. It starts all the way over here. Now, you might look at this and recognize this angle as 180 degrees, but we want to report this in radians, so instead of 180 degrees, we're going to report the hour hand's initial position as the equivalent in radians, which is pi. We don't know what its final position is either, but what we do know is that these two positions are equal at this moment in the future. And that is actually what we're going to do here. We are going to set the final position of the hour hand equal to the final position of the minute hand, and we're going to calculate the time at which this occurs. Unfortunately, in order to do so, though we're taking advantage of our knowledge of these, we still don't know anything about their velocities. This is where we have to use our knowledge about clocks. A minute hand completes one full cycle in an hour. So its initial velocity is one revolution, which is 2 pi radians, in 1 hour. Now, we actually need to convert that. I'm going to do that down here, 2 pi radians per hour. We need to convert that to radians per second, and I know that 1 hour is 3,600 seconds. So 2 times pi divided by 3,600 seconds gives me, small number, 1.74, actually 75, times 10 to the negative 3 radians per second. Yeah. I then have to do the same thing, but for the hour hand. The thing is, the hour hand moves much more slowly. If it starts off at midnight, it takes a full 12 hours for it to make its way all the way around. So it covers 2 pi radians in 12 hours. I'm going to get out of the way here. 2 pi divided by 12 radians per hour multiplied by 1 hour divided by 3,600 seconds gives me that same number, but divided by 12, or 1.45 times 10 to the minus 4 radians per second. So those are my actual initial velocities, at which point I have all of the information I need. I can use this equation right here. The initial position of the hour hand plus the initial velocity of the hour hand times time equals the initial position of the minute hand plus the initial velocity of the minute hand times time. I want to get my time on one side, so I'm going to subtract the initial positions from one another. That's going to be omega for the minute hand times time minus omega for the hour hand times time. Factor that time out. And at this point, I can plug in my values and get a result. The theta for the hour hand, it started off at pi. The minute hand started off at 0. The minute hand was 1.75 times 10 to the minus 3. That's minus 1.45 times 10 to the minus 4. This is going to give me a number, so I'm going to divide both sides by that. So it's pi divided by the difference between those two numbers. Oops, try that again. Pi divided by 1.75 minus 1.4, assuming I get the correct sig figs. This gives me a time, sorry about that, time of 1,963.6 seconds. I can convert that into hours by dividing by 3,600, or approximately 0. Actually, let's convert that into minutes instead. So I just take that number and I divide it by 60, which gives me 32.7 minutes. And so the answer to my question is that it is 32.7 minutes later, also known as 6, call it 33, is the time when the two clock hands will be at the same place again. So see, this problem was actually very challenging because we were given very little information. This is also about as challenging as you can expect these problems to get because of how little information you're given. Okay. In the last couple of minutes here, I just want to tie all of this together. I really want to connect the material that we covered in previous chapters to the ones covered here. Now, you'll probably have noticed that we have very similar quantities: displacement versus angular displacement, velocity versus angular velocity, acceleration versus angular acceleration. It's worth asking if there's any way we could connect these things together somehow. To see how, let's consider circular motion. Now, it turns out that circular motion, like the sort we dealt with before, where we have an object sort of rotating around, we could calculate how far it's traveled by using its arc length. And this right here tells us how to translate an angular distance, theta, to a physical distance, s. It's just theta times the radius of the circle. Now, it turns out there's a similar relationship for velocities. The angular velocity, the rate at which it goes around the circle in radians per second, can be converted to a regular velocity, v, simply by multiplying by this radius. So in the same way that the arc length is radius times angular position, angular displacement rather, the velocity is equal to the radius times the angular velocity. But it's worth noting that this velocity is the tangential velocity. It is the velocity that is perpendicular to the radius as you go around the circle. It's what you would use in the centripetal acceleration formula. We can do a similar thing for acceleration as well, except there's a trick here. We've actually already talked about acceleration in circular motion, and we determined that the centripetal acceleration, which always points in towards the center of the circle, which is given by v squared over r, that's something we already know about. That is something that already exists from our point of view. Now, it is worth mentioning that this v squared over r, I can use that relationship I just wrote down, that v is equal to r times omega. This is going to give me r squared omega squared over r, or just r omega squared. So I can actually rewrite my centripetal acceleration from v squared over r as r times omega squared. This is going to be useful in this chapter. But that is the acceleration that's in towards the center. It is theoretically possible, and we have already seen this on one homework problem, for in addition to the object's direction changing, its speed might be changing as well. There is thus a tangential acceleration that we can consider. We calculate it using a similar formula. It's just alpha times r. But if we were to ever ask about the total acceleration, we would have to add these two components as vectors, meaning we'd have to use Pythagorean's theorem. So just keep that in mind. With that said, we are officially, and then the way we understand both of these things is that the centripetal acceleration is why the direction of an object's velocity is changing, and the tangential acceleration would be why its magnitude is changing. With that said, we are done with the first part of Chapter 8. We are done with rotational kinematics. I suggest you go take a crack at some of the problems on the homework when you can, after you've done your exam prep and after maybe you've taken your exam on Wednesday. There is no lecture on Wednesday, but on Friday we're going to pick up with rotational kinetic energy, and we are going to go from there. Now, I do have office hours available. Walk-ins will start in about 10 minutes, and then I do have some appointments left this afternoon. If you are worried about the exam and you'd like to chat about strategies, I am booked pretty solid from 1 to 3, but I think I have some time after 3 that's still available. Let me know. Otherwise, good luck, and I will see you on Wednesday for your exam. Have a great day, folks.